Welcome to Pomodoro Joe for Thursday, April 13th, 2023. Today we're doing LeetCode problem 946, validate stack sequences. It's a medium problem. And the problem statement says, given two integer arrays, pushed and popped, each with distinct values, return true if this could have been the result of a sequence of push and pop operations on an initially empty stack, or false otherwise. All right, then they have some examples here. I don't think we even need to go through the examples and some constraints. All right, so it's good to know popped is a permutation of pushed, so that's good to know. And all elements of pushed are unique, which is also important. So we don't have to worry about like branching or making a decision about whether or not this pop is legitimate. Okay. So we'll put 25 minutes on the Pomodoro timer and get started. So I think to solve this one, we'll just do pretty much what it says. We will create a stack and we will push things on the stack from our pushed list, and then we'll pop things off the stack using our popped list. Then at the end, we can check to see if we've popped everything in our stack. We don't actually have to pop everything in the stack. We just have to make sure we get to the end of the popped list. If we get to the end of the popped list, then this was a valid push-pop pairing. If we can't get to the end of our popped list, well then this wasn't a valid pairing and we return false. Okay, so with that, we will start by creating a stack. Now in Python, you can create a stack with just a list. So we have an empty list as our stack. Then we'll go through every element in our pushed. So our pushed is going to be the easy one. Basically, you can always push things onto the stack. That's no problem. Now, popped is where it gets a little tricky because you can only pop things off the top of the stack, and popped is telling us what value it's expecting. So we basically have to look at the top of our stack to see if it matches what value we're expecting to pop. Okay, so let's see. For every, I'll just call it n in pushed. So we'll just push this onto our stack. So we can do that by appending. Okay, so we've pushed something onto the stack. Now we want to check to see, can we pop this off the stack? Or is this the thing we're expecting to pop off the stack? So let's see. Well, let's check the popped. Now I need to keep track of where in the popped list I am. So let's keep an index. So we'll have pop index. And we'll set that to 0. All right, so we will say if the pop at pop index is equal to whatever is at the top of our stack. So that's going to be stack at -1. So if it is equal, then we'll want to pop it. Because we know that these are unique values, we know we need to pop things in our pop list. So we can only do that when it's on the top of the stack. So if it is the top of the stack, we will pop it. So we'll just say stack dot pop. And I like to do -1 to show that we're popping at the end of our stack or the top of the stack. I think -1 is the default, so you don't really need to put it. And then we will need to advance our index. So pop index plus equals 1. All right. So let's see, we'll go through our pushed list. We'll push things onto our stack. If the number we're looking for in our popped list is at the top of the stack, we'll pop it and go to the next number in our popped list. One other thing we're not checking here, which I should check, if we have a stack at all. So we need to make sure that there is something in our stack before we can check the top of it. So if stack and the popped at pop index is equal to that top number on stack. Now let's see. I don't think it's enough to do this just once though, because once we pop something off the stack, there is a new value at the top of the stack, which might match our new value in the popped list. So we basically want to say while we have a stack and the popped at index, pop index is equal to the top of our stack, then we'll keep popping. So essentially, we'll just keep popping things off until we no longer have a matching pair or we run out of things to pop. Okay, Let's see, and then we'll keep pushing things onto our stack. Eventually that will run out and we can return. So at this point we return, well, what do we return? We want to make sure that we made it through our entire popped list. So we'll return true if, let's see, I guess we're looking for pop index. If that's equal to the length of our popped list. Otherwise, we'll have to return false. Means that we still had something left in our popped list that we were not able to pop out of the stack. I think this is it. Let's see how it goes. All right, still passes. Let's see if we can pass all the runtime checks. And we pass. We only beat 36% for runtime, but we beat 85% for memory, so that's not too bad. What can we do to make this faster? Because this is pretty slim. There's not a lot going on in here. There are a couple things we can do to make this faster. One, we can change some of these names. That does actually make a difference sometimes. We can also get rid of some of these white spaces. Doesn't make it any clearer to read though. So let's see, what else can we do? That actually made it slower. Huh, surprising. All right, let's undo those then. All right, one thing we can do. So this stack right now, we're just using a standard Python list. Now there's another type of data structure that Python offers called a deque. That's spelled D-E-Q-U-E. Now a deque is essentially a list that is really good at pushing and popping. It's meant for queues and for stacks. So it's going to be optimized for this exact type of thing. So let's try using a deque. Now, I can't guarantee this will be any faster. I haven't tried this, but it's worth a shot. So instead of using a list, we'll use a deque. Now, you have to construct a new deque, store it in our stack. Now, we still have the same append, but instead of this pop, we have just a standard pop. All right, I think that should do it. Let's see how this goes. Okay, still works. Let's see if this saves us anything. And that makes a huge difference. Look at that. By changing from a standard Python list to our deque, we went from a 38% up to a 97% for runtime and a 34% for memory. So using a deque is definitely the way to go on this type of problem. All right, I don't think I can do any better than that, so I'm going to leave it there. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.